So our next section that we're going to go through is polar coordinates and then also curves. So the idea with this is we know our unit circle route moves in very circular motions. We're now going to define a system for that. So instead of writing our points as an x and y, we're going to have some radius of a circle to go past the unit circle, and then we're going to have an angle associated to it. So we're still going to have a system that looks like it was the x and y, but instead we're going to not label that as x and y. This is going to be our starting axis, just like it is when we build our unit circle. So this is called the polar axis. And then our origin is replaced by something called the pole, okay? So what happens is you have a radius and you have an angle. You can have negative for both of these things. A negative angle does exactly what you would think. Instead of moving around our unit circle or a circle like this, a negative angle tells you to move in the clockwise direction. A negative radius is a little bit harder. So the idea is once you plot a point, say you have one right here, this is defined by r and theta. R is going to be the distance out to that point. So it's the radius of the circle it lies on. And then theta is, again, that angle that it makes with the polar axis. Okay? So positive theta moves in this direction. Negative theta moves in this direction. If you have a negative radius, what you're going to do is you're going to plot your point like normal. But once you do, we do what's called shooting through the pole. So if this were my point here, my point with a negative radius would shoot through the pole and land on the exact opposite side. And this angle here would be the same one as your theta value, okay? So this point down here would actually be the same, but with negative r. So the coordinates for this one would be negative r and still that same theta value, okay? So it ends up forming a straight line directly through the pole. The problem with doing these is just like on the unit circle, the points are not necessarily unique because we can move in that circular motion. So the same point can be represented in a multitude of ways. And likewise, because we also have negative angles and negative radii, you can plot those points in a ton of different ways, okay? So before we start working with kind of converting things back and forth, let's just get some practice plotting the points whose polar coordinates are given. So the first coordinate is my radius. So at most I need a circle of radius 3. So I'm going to just count these circles as a radius of 1. Our starting angle is 0. This is 90 degrees, which is pi over 2. This is pi, and then this is 3 pi over 2. You can plot intermittent ones as well, so you can plot your 30, 60, 90 if you want. I'm going to go ahead and plot 45-degree angles as well. And I'm going to go ahead and turn these into dotted lines to just make them match. So this angle here would be pi over 4. This would be 3 pi over 4, 5 pi over 4, and 7 pi over 4. So starting out with point A, both my radius and my angle are positive. So I always start by plotting the angle. I go up 2 pi over 4, which would land me somewhere along this line. And my radius is 3, so I go out to my circle of radius 3. So point A lands me right here, okay? For point B, I still plot it like normal. I ignore my minus sign. 3 pi over 4 would land me right here. But because my radius is negative, that tells me I go on a straight line and I shoot through the pole and I land exactly on the opposite side. So point B would be down here on the circle of radius 3. Okay. For point C, I have a positive radius, but I have a negative angle. So I start at this circle, or I start at the polar axis, and then I go down pi over 2. So that would land me right here, and I'm on that circle of radius 1. So point C is right here. Okay. Then finally, point D has both being negative. Again, I'm going to start by plotting the angle. We go down to negative pi over 2. The circle of radius 1 would be right here, but because my radius is negative, I go in a straight line and shoot through the pole, and I land right back up here. Okay. So tons of ways that we can represent each of these, because you could see point D we could also represent by 1 positive pi over 2. Or I can go back negative 3 pi over 2, positive 1. Tons of ways to get to exactly that same point. Okay. What we're going to focus on now is we're going to look at how can I convert back and forth. Because we still have our normal xy axis, and we know there's a strong connection between circles and triangles and our trig functions. So we're going to look at a way to convert from polar to Cartesian and also Cartesian to polar. So if we look at our connections, again, you can call these the xy axes, but it's also our polar axis, and then we have that one to just indicate our 90-degree angles. Every single point that we plot in polar is represented by some r theta value, which can be converted to some xy value. So with our polar, we have just the angle, and then our value of r. And then for our Cartesian, we have that right triangle, which gives us x and y. So if I'm starting in polar and I'm given r and theta, I want a way to convert to x and y. So that's where we can use our triangle. If I look at cosine of theta, it's adjacent over hypotenuse. So cosine of theta is equal to x divided by r. And just rearranging that gives us our x is equivalent to r cosine of theta. So if I know r and theta, I can convert to x easily. And then likewise, the other corresponding one is if I look at sine of theta, it's opposite over hypotenuse. So that's y over r. And then just multiplying by r gives us y equals r sine of theta. Okay. So pretty straightforward, just plug in the value of r and theta. If instead I'm given x and y and I want to get to what is r and theta, well, to connect r with x and y, we can just use Pythagorean theorem. So we use x squared plus y squared is equal to r squared. The angle is a little bit difficult to do. So if you want to just relate theta to y and x, then really the only way we have to do that is either with tangent or cotangent. So tangent of theta is opposite over adjacent. Okay. So this would require you to be able to recognize what tangent is. But again, you can always break that as sines and cosines. So realistically, you can also utilize these formulas and figure out, okay, well, for what angle is cosine this, and for what angle is sine is this. And then you'll be able to make that connection, okay? And then also with this one, when you're solving for r, when you take a square root, remember technically you get a plus or minus. So it depends on what you're asked. You might want your r to be positive. You might want your r to be negative. So in either case, you'd have to work out what the correct theta value is for that, okay? So we'll start with this first example. It's given in polar. We want to convert to Cartesian. So this tells us our radius of our circle is negative root 2, and our theta value is 5 pi over 4. Okay. Just to get some familiarity practicing this, and then we can also verify, yes, we find the right x and y values. You can definitely go ahead and plot this. So here would be 0, here would be pi. My theta being 5 pi over 4 would take me past into quadrant 3. So ultimately, we would go all the way around to right here. but then our radius is negative. So that tells us we shoot through the pole and we land back here. So this is negative root 2, 5 pi over 4. Okay. So we're cutting through at a straight line, which again is really 180 degrees. So if I want to find x, that's equal to r cosine of theta. My r is negative root 2, and then theta is 5 pi over 4. Okay. And so again, if you think about where 5 pi over 4 is, that's down here in quadrant 3. A pi over 4 angle is a root 2 over 2. So this would be negative root 2 over 2. Multiplying those out, the negative cancels. Root 2 times root 2 leaves you with 2. And so 2 divided by 2 is 1. So our x coordinate is going to be 1, which makes sense because, again, that point lands in quadrant 1. And likewise, when we go to find y, it's equal to r sine theta. So it's negative root 2 sine of 5 pi over 4. And then again, because you're a pi over 4 angle, it's a root 2 over 2. We are in quadrant 3 with this angle, so sine is negative. So it really ends up being exactly the same thing. So this results in positive 1. So this coordinate in Cartesian form is given by 1, 1. Okay. We'll try another one of these where we want to convert to polar. And so again, I always like to go through and I like to plot my points first, just because I think that helps out a ton. Okay. So both of my coordinates are negative. That tells me that this point is somewhere here in quadrant 3. Okay. So I don't know exactly where, somewhere roughly around here, but that's negative root 3 over 2, negative 3/2. Okay. So I'm going to start by finding my value of r. So in this case, I know x squared plus y squared is r squared. My x is negative root 3 over 2. My y is negative 3 over 2. Okay. So going through with that, then I've got root 3 times itself gives me positive 3. And then I get 4 in the bottom. And then for that, that gives me positive 9. And then divided by 4. Okay. Adding those together gives us 12 over 4 is r squared. And that at least divides nicely. 12 divided by 4 is 3. So 3 is my value of r squared. So I get two possibilities. I get root 3 or I get negative root 3. Okay. So again, it solely depends on the directions itself as to which example you want to do. I want to show you, though, both of these points because you're going to need to know how to find the angle with a positive radius and also how to find the angle with a negative radius. So we'll try when the angle is positive first. Okay. So in that case, my theta value would land me exactly here. So theta should be something between 180 degrees and 270. Okay. And I know tangent of theta is going to be y over x. My y value is negative 3/2. My x value is negative root 3 over 2. And so that minus minus cancels, and so does the 2. This is 3 over root 3. Okay. But that definitely is not pretty. So, and I'd have to pick off exactly what function or what angle gives me this for tangent. So if we go ahead and rationalize this, this would be 3 root 3 over 3, which is the same thing as root 3 over 1. Okay. Technically, it's just root 3, and you could refer back to your chart to figure that out. But if you're not super comfortable with tangent especially, then what I would recommend doing is saying, okay, well, this is my value here. Well, if I divide top and bottom by 2, that looks a lot nicer because this needs to be sine of theta, this needs to be cosine of theta. If I think the reference angle that gives me sine of theta being root 3 over 2, that tells me it's going to be a 60-degree angle because my cosine is going to be 1/2. So in that case, I know my reference angle here is 60 degrees, and I'm looking for the angle in quadrant 3. So I would go forward 60 degrees. That would land me at 4 pi over 3. Okay. So that would be the angle that I'm searching for. So when r is equal to root 3, then my theta value is going to be 4 pi over 3. Okay. So this coordinate would be given by root 3, 4 pi over 3. Okay. So that's one way to represent our point in polar. However, we can also consider our r value to be negative. So I'm going to go ahead and delete this just so I have some room within here. We'll move this over, move this over, and now let's try the same thing, but with our r being negative. Okay. So this one's more complicated because my r is negative. That tells me I'd have to shoot through the pole after I plot the angle. So essentially, if I were thinking about this, I need to land here. So I need to find the angle in this quadrant so that when I plot this point here, I then shoot through the pole and get to the other side. Okay. So this angle and this one are exactly the same. And we know this reference angle is 60 degrees, which is a pi over 3. So that tells me my theta value has to equal pi over 3. Okay. So in this point, if my radius is negative, then the angle I need to pick would be positive pi over 3. So this way, when I shoot through the pole, I land back there. It's always going to be a difference of pi, because if I take 4 pi over 3 and I subtract pi to get back to this angle, that lands me at pi over 3. Okay. So now that we have a little bit of a hang of working with this polar coordinate system, we want to talk about what do graphs look like in this. So these are called polar curves. So typically the form for your polar curves is you have your r by itself, and then you have some function of theta over here. And in the same way that we can convert points back and forth, we can also convert a lot of our equations. So we're going to start with just some nicer examples, but then we're going to talk about special types of curves that have names. So we're going to start with this first example. We're going to sketch the curve r equals 3. Well, if you think about that, theta isn't involved at all. So a lot of times the way I like to go about these is I like to pick angle values and then figure out what does r need to be. But in this case, no matter the angle you pick, your radius is 3. So when r is 0, when theta is 0, r is 3. When r is pi over 2, I can't talk right now. When theta is pi over 2, r is 3. When theta is pi, my radius is 3. When theta is 3 pi over 2, my radius is still 3. And when theta is 2 pi, my radius is 3. So if I go ahead and I plot this, and I make each of these circles a radius of 1, when theta is 0, my radius is 3, so that lands me right here. Pi over 2, my radius is still 3. Pi, my radius is still 3. And 3 pi over 2, my radius is still 3. And then you can pick all of those intermittent angles, but every single time we have a radius of 3. So ultimately, I just get a circle of radius 3. So we can definitely connect this to our equation in Cartesian for a circle of radius 3. Well, if r is equal to 3, then r squared is equal to 3 squared. R squared, however, is x squared plus y squared. And so you get exactly a circle centered at 0, 0 with a radius of 3. Okay? Let's try a different example where r is equal to -2 sine of theta. And again, if I don't know what the shape is to start, I'm going to pick theta values and I'm going to see what r is equal to. Okay. However, because I have done this plenty of times before, I know what these shapes are. So I'm definitely going to start at 0. If I plug in 0, well, sine of 0 is 0, so my radius will be 0. Meaning we start right here at the pole. Okay? I'm going to make each of these a distance of 1. Then I'm going to go ahead and I'm going to pick an angle in between, because if you think about the sine function, it's got those peaks at all of the quadrantal angles, but they repeat themselves. So what I'm going to do is I'm going to pick some intermittent ones just to make life a little bit easier so I can fully see this picture. So if I plug in pi over 4, sine of pi over 4 would be root 2 over 2. Timesing that by -2 gives you negative root 2. So that's about 1.4. So I'd plot the 45-degree angle, but my radius is negative, so that tells me to shoot through the pole, and it lands back here. So this would be roughly our point for pi over 4. Okay. If I plug in pi over 2, sine of pi over 2 is 1. So that gives me -2 as my value of r. So if I plot my 90-degree angle, that's right here, but my radius is negative. So really we shoot through the pole and land here. If I plot 3 pi over 4, well, sine of 3 pi over 4 is positive root 2 over 2. So this ends up being exactly the same thing as pi over 4. 3 pi over 4 would land me back here, but again, I shoot through the pole, land on the other side around the same spot. And then when we plug in pi, sine of pi is 0. So really I'd plot over here, but my radius is 0. It just lands me back at the pole. So really what happens is I started at this point and I would keep going, and then I'd come back to the pole. Okay. So it's not perfect, but this actually ends up being a circle. So to show you that we can convert this, I don't want to square both sides because I have no idea how to deal with sine squared, but I do want to get r squared. So instead I'm going to multiply the equation by r. That gives me r squared is equal to -2 r sine of theta. Well, r squared is x squared plus y squared, and then r sine of theta is exactly 2y. So I can move that over to the other side to get plus 2y, and I'd be left with nothing over here. And then I want to be able to factor this. So if you remember going through and completing the square, I would need a 1 here to make that y plus 1 squared. And this is fantastic because this is a circle. It's centered at 0, -1. And our radius is 1. And that's exactly what we have. Centered at 0, -1. So again, didn't draw this super nice to scale. That's okay. But then we have a circle of radius 1. Okay. So if I change this to cosine, it would just be moved along the x-axis. And because it's -2 sine, it takes up the bottom part of that axis. Okay. For this next one, we, instead of having anything dealing with r, we just have theta equals pi over 4. So your angle is fixed in this case, but your r can be whatever it wants. So I'm going to go ahead and give these some numbers. But if I pick my r to be 0, we would just go through the pole. If I pick my r to be 1, that would give us a 45-degree angle. So this would be 1 pi over 4. If I pick my r to be 2, we'd land right here, and 3, we'd land right here. So I can pick whatever theta value I want, or sorry, I can pick whatever r value I want, but my theta has to be pi over 4. But I can also pick my r to be negative. So not only do I get those points, but if I pick -1 instead, I would shoot through the pole and land back here. So this would be the point -1 pi over 4. And likewise, this would be -2 pi over 4. And this would be -3 pi over 4. So you really get all of these points as well. So what you end up getting is really a straight line through the origin, or the pole. And this angle it makes is pi over 4, which is 45 degrees. So this would just be the equation y equals x. But to show you that is the equation, again, our connection to get rid of theta is we know tangent of theta is y divided by x. Wrote that backwards for a second. And then theta is fixed at pi over 4. And tangent of pi over 4 is 1. So just rearranging that, you get x equals y, which in a nicer form is y equals x. So it is just directly through the origin. Okay. So I got one more of these before we talk about all of our special curves. And this is r is equal to 11 secant of theta. Now I can sit here and I can plug in theta values that I know how to evaluate secant at, but it is definitely a little bit tedious to do. So instead, what I'm going to do is show you the Cartesian form of this, and then the polar curve is exactly the same. I have no idea how to change secant over. Remember, secant is 1 over cosine. So from here, I can go ahead and multiply both sides by cosine of theta. And so that gives me r cosine of theta is 11. Well, r cosine of theta is x. So this is really just a vertical line, x equals 11. So it would go through a point right here. If I plugged in 0 as my theta value, secant of 0 is 1, so your radius is 11. And then you just get a straight vertical line through. Okay. So if you want to always convert that equation first, in the cases that you can, absolutely go through. But if all else fails, making a table like this is really helpful. And it's especially helpful when we start talking about these special curves. So let's start with our first special type of curve, which is called a rose curve. The way you're going to be able to distinguish that you have a rose curve is that you have some number times theta on the inside. This is just going to give you some length and stretch out the radius, but this value in here is how you determine a rose curve. The reason for that, you'll see when we draw it, is there are petals. So based on the value of n, it tells you how many petals there are. If n is an even number, so say you have 4 theta on the inside, then there are 2 times that number of petals. So 4 theta would be a flower or a rose with 8 petals. If that number inside is odd, then there are exactly that many petals. Okay, so if it's sine of 5 theta, it'd be a 5-petaled rose curve. These curves are basically going to look like this. So this would be one with 5 petals. All the petals should be uniform in shape, but obviously I'm not going to be the best drawer for this. But this would be something like cosine of 5 theta or sine of 5 theta. And the number out front just stretches and tells you what is the maximum point of that rose. Okay. So what we're going to do to draw these is we're actually going to utilize drawing our normal 3 sine of 2x curve instead. So we're going to graph it in r theta plane, and then I'm going to utilize that to be able to get the picture in my polar curve instead. So we'll start by graphing this in an r theta plane. So again, treating it as we normally would, okay? So if we were to graph 3 sine of 2 theta, our theta is replacing x, and then r is replacing y. That 3 out front is that amplitude. And remember, this alters the period, okay? So the period of this sine curve is 2 pi over b. Well, in that case, my pi value is 2, so my period is going to be pi, okay? And again, this is a rose curve. Because r is equal to 2, the result will be a rose curve with 4 petals. So essentially what's going to happen is you're going to form a petal when your radius starts at 0 and comes back and ends at 0, because that's going to go through the pole. If r is equal to 0, your point is at the pole. So I need to figure out on my r theta plane for which angles do I form a petal. Okay. So if I think about my period being pi, I would go through a normal sine graph in that stage. So this angle would be pi over 2, this would be pi over 4, and the other one would be 3 pi over 4. Just so I don't muddy it up, we're going to avoid that. My sine graph starts at 0, then it goes up to the peak, back to 0, down to the peak down there, and then back to 0. Okay? So my rose or my sine curve would look like this. So what happens is my first petal is going to be formed between 0 and pi over 2. Then my next petal will be formed between 0 and pi. However, I need to get 4 petals. So really, I'm going to have to go through graphing this over a length of 2 pi, because that would be 1 revolution around our polar curve. So really, this gets copy and pasted. Halfway in between pi and 2 pi is 3 pi over 2. And then those 45-degree angles would be important. But then our graph repeats. Peak, 0. Peak, 0. And your curve goes here, okay? So now I want to translate this to my polar curve. So let's go ahead and get that drawn first. So I've got my curve. Here would be 0. This would be pi over 2, pi, 3 pi over 2. And then I need to go out to a peak of 3, okay? So my first petal, I start at 0. At pi over 4, I hit the peak. And then at pi over 2, I come back. So I start at 0. At pi over 4, 45 degrees, I hit my peak value. My radius at that point is getting bigger and bigger and bigger as my angle gets bigger. And then I'm going to come back to the pole. So my first petal is formed over that interval from 0 to pi over 2. For this second interval, that would be pi over 2 to pi, that's right here. All of those r values are negative. So instead of actually forming the petal in this quadrant, all of those points get shot through the pole, and you'd form this one, okay? Because the idea is you start, you go out, you go out, you go out, and everything should be nice and smooth. I shouldn't have a jagged change. Instead, I come into the pole, and then I have a nice smooth transition to form this other petal over here. So if you think about plotting this point here, that would be at 3 pi over 4, but my radius is -3, so it gets shot through the pole. Okay, so my second petal is formed here. So again, you follow it smoothly, 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 transition smoothly, smoothly, smoothly. And again, to be nice and smooth, I'm going to have to form this quadrant next, and then I will form this final petal. So my next petal occurs between pi and 3 pi over 2, which is here in quadrant 3, and my radius is positive, so that's good. This happens at that 45-degree angle, and your R is positive. So your next petal is formed here. And then our final petal is formed between 3 pi over 2 and 2 pi, which would be in this quadrant. But again, that radius being negative gives you the petal formed back here. Okay. So again, it's nice fluid transitions. We go into here, we don't make a sharp turn. We come into this quadrant, into this quadrant, and then back up here. And then you would really just keep repeating itself if you were to pick more angles. So it gives you nice smooth transitions. If you graph a cosine, all that happens is you might have the start of your petal formed up here. And so you'd actually end up taking root on those axes instead. Okay. So making it a sine or cosine is just going to shift that petal around. If you have an odd number of petals, again, to fit everything in nicely, you're going to have maybe some kind of looking like this. It depends on the specific problem. So it's always really helpful to draw it in an r theta plane first. Okay. The very last special type of polar curve we're going to talk about are cardioids and limicons. And so what's going to happen here is you're going to have a cosine or sine function, and you're going to be adding or subtracting that with some number. Really what's going to occur is if you're dealing with a cosine function, it's telling you you're going to take up most of your what's considered to be x-axis, because that's what cosine deals with. If you're dealing with the sine function, most of your graph is mostly going to lie on the y-axis. So it's either going to be up in the top here mostly or up in the bottom. Okay. If it's positive, it takes up the positive side of that axis. If it's negative, it takes up the negative side. So in this case, both of these deal with a cosine. This positive would tell you the graph would take up most of the positive x-axis. And then if it's minus, the graph would take up most of the negative x-axis. And then it's equivalent when you deal with the sine function. Instead, it's taking up the y-axis. The numbers in front here, like in this case, they're both 1 and equivalent. That's going to determine the shape. So there are 4 possibilities as to what could happen. The first is if the value of A is smaller than B, you're going to end up with the only shape that has an inner circle. So I'll show you how you can distinguish that you're in this case. So your graph is going to look something like this. This is called a limicon with an inner loop. If the two values are equal, this is the only one that's going to have a sharp point. And it kind of looks like a tomato with the point on the inside, but it also has like a heart shape. These are called cardioids. And then if the number in front is bigger, this is going to result from having a negative radius. So it's the only one where you'll see will have a negative value. And that's because if you have 1 minus 2 cosine theta, that results in negative. But if the number in front is bigger, there's no way you're going to have a negative radius. So you're going to have 1 or 2 shapes here. They do look very similar. This one will be similar to a cardioid, but it doesn't have a sharp point. Okay. this sharp point is going to occur at the pole. So this will be a dimpled limacon. And then the other option is, instead of it being dimpled in, it's kind of pointed and curved outwards. So you can get a dimpled or a convex limacon. So I'm going to focus on these two examples because, again, these ones you'll be able to just plot all of those angles and see what's going on. But these are the two special cases that will occur. So we're going to do one example of each of those. We'll graph 1 plus 2 sine theta, and then we'll graph 3 minus 3 cosine. So this being positive sine tells me my shape is mostly going to be on the positive y-axis. For these, I'm only going to need to worry about plotting those quadrantal angles. So 0, pi over 2, pi, 3 pi over 2, and then back to 2 pi. Okay. If I plug in 0 for sine, that gives me 0, so my radius will be 1. If I plug in pi over 2, sine of pi over 2 is 1, so that gives me 1 plus 2 times 1, so my radius would be 3. Sine of pi is 0, so that will be 1. When you plug in 3 pi over 2, sine of 3 pi over 2 is negative 1. So this would be 1 minus 2, resulting in negative 1. And then 2 pi will land you back at 1. Okay. So we'll go ahead and we'll plot these points and we'll see how it makes the shape we want. So when my theta is 0, my r value is 1. So I'm going to treat each of these as 1. When theta is pi over 2, my r value is 3. At pi, it's 1. And now at 3 pi over 2, the radius is 1, but we have to shoot through the pole. So we actually land back up here. And then 2 pi lands us at the start. So the way this happens is we go and we can continue up to this point. We have to come back down. But now to get this point up here, at some point we'd have to cross, and then we'd have to come back down over here. Okay, so that's how that inner loop is formed. Essentially what happens is, if you were to plot these values, you'll see this 1, remember, shifts it upwards. So you'd be trapped between 3 and negative 1 instead of negative 2 and 2. And your sine graph would look like this. And so between these two values is when that inner loop is formed. And so it happens somewhere between pi and 2 pi. Okay. So that is our limacon with the inner loop. Again, it's the only one that's going to have a negative radius because this value is bigger. If it was this value that was bigger, even when this is the max at negative 1, 4 minus 2 would give you positive 2, so you'd end up with a point down here, and you wouldn't have that same shape. Okay. So let's just try one more of these. In this case, these are exactly the same. And then if I look, this is negative cosine of theta, so I'm going to take up most of the negative x-axis. Again, I just need to pick those same quadrantal angles. So 0, pi over 2, pi, 3 pi over 2, and 2 pi. If you plug in 0, cosine of 0 is 1, so that gives you 3 minus 3, which is 0. If I plug in pi over 2, cosine of pi over 2 is nothing, so my r is 3. If I plug in pi, that value is negative 3, so this turns into 6. Cosine of 3 pi over 2 is nothing, so r is 3. And then cosine of 2 pi is 1, so you get 3 minus 3 again, which is 0. So I need to go out to 6, so I'm going to go ahead and count these by 2. So our starting point is going to be right at the pole. At pi over 2, our radius is 3. And so in between those, we connect the dots. Then at pi, our radius is 6. So again, go back and connect the dots. 3 pi over 2, it's negative, or 3 pi over 2, it's 3. So we go and connect, and then we have to come back to the origin so we get that nice symmetric shape. All of these are going to have nice symmetry. But you can see this is called a cardioid. This one looks a little bit more heart-like. So this is the only one that's going to go through the pole as a nice sharp turn. This does go through the pole, but to form that inner loop. When they're exactly the same, you will have just one sharp point, okay? So all of these, you're going to be able to just use the quadrantal angles to find a good picture.